In this lecture, we're going to talk about X-rays, X-ray diffraction, and the Compton effect. So X-rays were discovered in the late 1800s, and after they were discovered, then they were identified as a type of electromagnetic radiation with very short wavelengths. X-ray wavelengths are typically about 1/10 of a nanometer, so very short wavelengths, which means also very high energy. And so X-rays have the ability to penetrate most materials with relative ease, which is why we use them for bone scans and things like that. They can penetrate the soft tissue of your body and then reflect off of the hard parts, your bones. Now, X-rays are produced when high-speed electrons are slowed down very suddenly. Often the way that we do this practically is by firing the electrons at a metal target. So in this image, what we have is we have our filament, which is essentially the source of our electrons, and we're going to shoot the electrons over here at this tungsten target. And this is all going to be in vacuum so that, there's nothing nothing for the electrons to interact with before they get to the tungsten target. So this heat that's generated by current in this filament here causes electrons to be emitted, and then the electrons are accelerated across. They hit this tungsten target, and then the target is held at a higher potential, meaning a higher voltage, so that the electrons are accelerated towards it. And then when the electrons hit, then what happens is X-rays are emitted. The electrons interact with the materials, with the atoms in the tungsten, and X-rays are emitted. And if we want to look at physically what's happening when the X-rays are emitted, we have our electrons. So here's our target atom. So we've hit this tungsten target, and so our electrons are going to pass very close to the target nucleus, to the tungsten atom nucleus, and they'll get deflected, because they're going to feel a force towards it and they get deflected. We can model this essentially as a collision. This is a similar principle to how we slingshot spacecrafts around Jupiter to reach the outer parts of the solar system. But our electron, as it is deflected, loses energy, and that energy is emitted in the form of an X-ray photon. And if the electron loses all of its energy, then essentially, it stops. And then you can completely form all of the energy of this electron into a photon. And so the wavelength of the emitted photon, the wavelength of the X-ray photon, can be given by E times delta V, where E is the charge of the electron, is going to equal the frequency times Planck's constant, or hc over the wavelength of the emitted X-ray. So when we do this and X-rays are emitted, then the X-ray spectrum is going to look like this. And the X-ray spectrum consists of kind of two main parts. You have this continuous broad spectrum, that's this bit down here. This is called Bremsstrahlung radiation. And what this looks like depends on the voltage across here, And these lines, these sharp lines, depend on whatever the target material is, So these sharp lines depend on whatever our target. And then this depends on the broad spectrum here, just depends on whatever voltage we have across from the filament to our target. And again, if we go back to here, our wavelengths or our frequencies that are emitted, and this is the maximum wavelength or the maximum frequency or the minimum wavelength emitted if the electron is completely stopped. It loses all of its kinetic energy in one collision. But obviously, that's not going to always be the case, Often, the electrons will undergo multiple collisions before they lose all of their energy. And again, that's what's going to give you this Bremsstrahlung broad spectrum feature of the X-ray spectrum, right? That lots of little collisions and the electron loses some energy with each one. That's where you get this Bremsstrahlung radiation. Now, because X-rays are an electromagnetic wave, they can do all the same things that other kinds of electromagnetic waves can do. They can do all the same things that light can do, including interference and diffraction. But remember, when we're talking about diffraction of light waves, that diffraction only occurs if the spacing between your lines, for instance, a diffraction grating, is approximately equal to the wavelength of the radiation being measured, which for visible light, right, visible light has wavelengths of approximately, right, 400 to 700 nanometers, or, 0.4 to 0.7 micrometers, which is approximately comparable to the width of a human hair. So doing diffraction, using diffraction gratings for visible light is not that difficult. But X-rays have wavelengths that are essentially 1,000 times shorter than visible lights, right? X-ray wavelengths are approximately 0.1 in the 0.1 nanometer range. So these are very, very short wavelengths. And so it's difficult to create a diffraction grating that you can do diffraction with X-rays. That said, atomic separations in crystals can act like a three-dimensional diffraction grating for X-rays. So the way this works is we're going to start over here in this image. So we have our X-ray tube, right, where we're going to form X-rays, create X-rays, emit X-rays, right, same as we talked about a minute ago. And then they're going to pass through this collimator, and basically what the collimator does is it just points all of the X-rays in this, only takes the X-rays that are traveling in this direction, right, so that they're all kind of hitting this crystal more or less parallel. Each ray is parallel to the other ones. And then the X-rays will pass through the crystal, and you get this diffraction pattern on your film over here. Now, often nowadays digital detectors are used, but the idea is the same. And the diffracted radiation is very intense in certain directions, right? You get this diffraction pattern just like you would for visible light in a diffraction grating, right? And again, the bright spots correspond to places where the X-rays are interfering constructively. Now, this array of spots here is called a Lau pattern, and I am probably mispronouncing that horribly, but it's L-A-U-E. And the crystal structure, so the reason that you do this is you do this to help determine the structure of the crystal, right, this crystal that you're passing this through. And that's determined by looking at, right, the positions and intensities of the various spots. And then you can use Bragg's law, which again is a way of characterizing constructive interference, more or less for a diffraction grating, but in this case, instead of a grating, we're using a crystal. And the way that works, right, so if this is my crystal, this would be a couple of layers of atoms in our crystal, right? So these are three-dimensional, so imagine a sheet that is extending into the screen and out of the screen, and then also stacked up. And what happens is you have your incident beam coming in, that's here, and the spaces between the atoms act like slits in a diffraction grating. And so they're going to reflect some off of the top, atoms on the top surface, some off of atoms off of the bottom surface. And you can work out essentially the atomic spacing, this crystalline structure, right? What are these distances? By using Bragg's law, which Bragg's law says that 2d sine theta is equal to m lambda for constructive interference. right? Constructive interference meaning the bright spots on your screen, right? And so your thetas would be these angles from the center, right? This one would be straight on, theta is equal to 0, and then you can measure all of your other thetas from there. And your d sine theta, right, is going to be, right, here is d, here is your theta, right? And so your 2d sine theta, and the reason it's 2 is because this one has to go down and come back out, is equal to m lambda. And again, m is just a number. It's our order number. M is an integer. It can be 1, 2, 3, however many. Now, another thing that we can study with X-rays is the Compton effect. Compton effect, discovered by Arthur Compton in, again, this was in early 20s, 1910s, 20s, thereabouts. And he worked at the University of Chicago. He got a Nobel Prize in 1927 for this work. But what he did was he directed a beam of X-rays toward a block of graphite being basically pencil lead. And what he found is that when X-rays were scattered, right, this whole diffraction pattern, that the scattered X-rays had a slightly longer wavelength than the incident X-rays, which means that the scattered X-rays, the ones that after they pass through the crystal, have less energy, right? Because remember, the energy of a photon is equal to hf or hc over lambda. And so if we have a longer wavelength, that means that our photons, our X-rays, have less energy. And the amount of energy that they lost depends on the angle at which they're scattered, right? So again, if we go back to our diffraction pattern where we had like our pattern where some of them were scattered at bigger angles and some of them are scattered at smaller angles, the amount of energy that they lost depends on the angle at which they were scattered. And this change in wavelength is called the Compton shift, right? This change in energy. So basically what's happened, if we go back to our diffraction picture from before, right? So if we go back to our diffraction picture, right, we have our incident beam, and that's essentially this, right? So this is colliding with this atom, and then it's being reflected, right? That's incident beam, reflected beam. In this picture, this is our incident beam, and this is our reflected beam. But what's happening is when this X-ray essentially hits that atom, it knocks off an electron and acts like, it just collides, right? Knocks off an electron. And so then the X-ray has less energy. The emitted X-ray, the reflected X-ray, has less energy than the incident X-ray. And this shift in wavelength, the difference in wavelength from this X-ray to that X-ray, is given by this equation, right? Our change in wavelength, the shift in wavelength, which is our lambda prime minus lambda initial, right, is h over the mass of an electron times c times 1 minus cosine of theta, where theta is the angle at which the X-ray is deflected, right? So this would be the angle on our screen from straight on that we would see our interference pattern. And essentially what this means, now this quantity here, h over mass of an electron times c, is called the Compton wavelength. And the Compton wavelength is equal to 0.00243 nanometers, right? This is a very small wavelength compared to visible light. And the thing to notice is that this Compton shift, right, how much our wavelength has increased, right? How much energy we've lost, because again, the energy is going to depend on this equation, only depends on the angle of the scattered X-ray and not on the wavelength of the scattered X-ray or the incoming wavelength of the X-ray. And this is evidence that for the photon, right, the particle nature of light. So previously we've talked about light having sort of a dual nature. And sometimes it acts like a particle and sometimes it acts like a wave. And interference and diffraction, that is light acting like a wave. But the photoelectric effect and this Compton scattering, that is light acting like a photon or a particle, right? We can essentially treat this as a collision where energy and momentum are conserved. So I'm going to cut this off here and I'll record another video for the next part of this, which is where we're going to talk about this duality, right? This dual nature of light.